Hello, welcome to the 7th lecture of this course. I'm currently on vacation in Jämtland in Sweden. In the background you see the town of Bräcke. So there will be a bit of noise because I had to go into the town to get good internet connection. But hopefully it works out. So let's start right away. Oops, there we go. So today's lecture is by vaccination and other preventive measures. And I will also talk a little bit about uncertainty estimates. So if when it is possible to obtain standard errors to estimates. So like earlier, I tend to do easier models and Michael tends to do more data-oriented analysis. So I think we complement each other well. I listened to his 2 lectures, which were very interesting to me. So you might pose the question, why is modeling at all of interest? It has been shown greatly this spring. And I would say that there are a couple of reasons. One is to increase the understanding of how an infectious disease spreads. Humans are always interested in understanding things better, but perhaps even more important is to be able to say something about prevention. So if you understand how disease spreads in a community, you sort of automatically also understand how it is possible to reduce spreading or prevent an outbreak. Much of what I will talk about today will be in terms of vaccination. I know many of you are interested in COVID-19. This is the ongoing big pandemic, and there is no vaccine. So I guess some things are not relevant, but you should sort of interpret vaccination in more general setting. It could be that the idea is that you immunize someone. So isolation is more or less the same thing as vaccination, because if you're isolated, you don't spread the disease onwards, so it has sort of the same effect. But I will talk a little bit about other preventive measures as well, and we will have this in the group discussion in the live session on Thursday. Anyway, suppose that we have a vaccine already before the outbreak takes place, for instance, the influenza, that's the case. And suppose that we vaccinate a fraction V before the epidemic season. And let's start off by assuming that our vaccine is perfect so that you obtain complete immunity. So if a fraction V have been vaccinated, they are initially immune. And this we discussed in an earlier lecture. So then the new reproduction number after vaccination, we call that RV, and it relates to the basic reproduction number as follows. RV equals R0 times 1 minus V, and the reason for that is that V are immune, so 1 minus V are the remaining susceptible population, so it is only so this is the average number of infectious contacts people have in the beginning of the outbreak, but only a fraction 1 minus V of these contacts will result in infections, since the other people are immune. So just as before, we avoid an outbreak if this new reproduction number is smaller than 1. That is the equivalent to saying that V should be larger than 1 minus 1 upon R0. So if we have vaccinated a fraction which is bigger than this, it means that there will not be a major outbreak, That is referred to as herd immunity, which means that not only are the vaccinated people protected, but also the rest of the community are protected, since there will be no major outbreak. There could be a few infections, but it will not take off with a big major outbreak. So this value here is called the critical vaccination coverage. So this is an important quantity, and I would say that it is one reason why knowing R0 is so important, because if you know R0, you also know how many you would have to vaccinate in order to prevent future outbreaks. So here's an exercise for you to compute, but I will not discuss that one further. And then on the next slide comes the critical vaccination coverage for some diseases. Of course, it should actually not only be for diseases, it should be in particular places, but here they have simplified lives saying that it applies pretty much to all regions, but have in mind that critical vaccination coverage as well as R0 depends on the disease, but also on the community. And we see that malaria has the highest vaccination coverage, measles has very high, smallpox, which is the only disease that has been eradicated, had the lowest critical vaccination coverage. So I would say that this is one reason why it was possible to eradicate smallpox from the world. Smallpox in Swedish is called smittkoppor. Chickenpox is vattkoppor, so that has also quite high critical vaccination coverage. So this level here, if you are interested, the directions to the Swedish health authorities is to each year vaccinate at least 95% of the newborns to measles. That comes from this relation because R0 is of the order of 15, so 1 minus 1 over 15 is 93%. Okay. Suppose now instead that the vaccine is not perfect, but that it has an efficacy, E. So E stands for efficacy. So what do I mean by that? That the relative risk of getting infected from an infectious contact is 1 minus E compared to if you don't have a vaccine. So if E is 1, this one is 0, so there's no risk at all. So you have a perfect vaccine. If E is 0, then there is no reduced risk. So E is the reduction from the vaccine, the reduction in risk of getting infected. So in more general settings for vaccine modeling, it is called VES, vaccine efficacy with regards to susceptibility. You can also have vaccine efficacy with regards to infectivity. So if you do get infected while you're vaccinated, it might also reduce your infectivity, but I will not talk about that in this course. The result extends if you don't have a perfect vaccine. The critical vaccination coverage is 1 minus 1 upon R0 as it before, but then you have to multiply by 1 over E. So we see that this quantity here, since E is between 0 and 1, this will increase the critical vaccination coverage. And it is in fact possible that if your vaccine is not so good, so it's not extremely close to 1, and R0 is quite high as if it is for measles, then this quantity here could actually exceed the value 1. So we could say that you have to vaccinate more than 100%. That is of course possible, but the meaning of this is that with this vaccine that is available, the vaccine cannot alone prevent an outbreak. So that's the interpretation. But for most diseases, this will be most diseases and vaccines. This will be smaller than 1, so it indicates how many you have to vaccinate. If I remember correctly, we showed earlier how to estimate R0. Remember now that we are in the simple setting, assuming a homogeneous community. And we showed earlier that an estimate of R0 was minus the logarithm of 1 minus the fraction infected divided by the fraction infected. This comes from the relation that, if you remember, the equation for the final size said 1 minus tau is equal to e to the minus R0 tau. So if you bring tau over here, and you take exponentiate both, and you bring the minus sign over here, and you exponent on both sides, you have 1 minus t is equal to e to the minus R0 tau. So this relation comes from a final size equation, but if you're a statistician, what you observe is how many that get infected, and you use this to estimate the basic reproduction number. And this formula here is valid only for a homogeneously mixing community. And now, on the previous slide, we had an expression for the critical vaccination coverage involving R0. So if we can estimate R0, we should be able to estimate the critical vaccination coverage if we know the efficacy. And let's first do this assuming a perfect vaccine. The perfect vaccine, we have this here. Critical vaccination coverage is 1 minus 1 upon R0. And we just insert the estimate here. And we get that we estimate the critical vaccination coverage by 1 minus 1 on the estimated value of R0. And we, okay, sorry, up here it is. And then we insert what that was. And if there was a fraction that was initially immune in the community where we observed the outbreak, there was a formula for that in my lecture some time ago. Then the only difference was that R0 was estimated differently. There was a 1 minus R as well. So now we have a train coming in the background. With some heavy stuff. Some metal things. But let me continue. I hope you hear me still. So then if the outbreak took place in a community where there was initial immunity, fraction small r was initially immune, then the estimate of the critical vaccination coverage looks like this. And if the vaccine is known to have an efficacy E, quite often the efficacy of a vaccine is known. That is usually evaluated before a vaccine can be put on market. Then the estimate of the critical vaccination is the one I showed previous slide, but multiplied by 1 over E. So there's an exercise doing that. So in general, my exercises are fairly easy, is the ambition, and I will put the solutions up. Not the solutions, but the answers. Those that have short to simple answers, I will put them up on the web page later. Let me now have one slide also on the endemic diseases. If you remember, endemic models was for the situation where a disease was present in the community for a long time, and suppose that there was no vaccine, so the population currently is not being vaccinated, and we are in a steady state, and what we observe is S tilde, which is the average age of infection divided by the average life length. And because we had a population in steady state, we assume this. This is also the same thing as the average fraction of susceptibles in the community. Remember that we are considering an SIR infectious disease, so you can only get infected once. So if, let's say, we take chickenpox, vattkoppor, maybe the average age of infection is 7, let's say it's 7.5 years. And suppose on average people live 75 years, then the average fraction in the community that are susceptible will be 10%, because if you get infected after 7.5 years and live 75 years, you will spend 10% of your life susceptible, and 90% of your time of your life you have already been infected by chickenpox. So S tilde is then the average age of infection divided by the average life length. And we showed that an estimate of R0 was 1 over S tilde. So in my numerical example, S tilde was 10%, so the estimate of R0 is 10, which I think agreed quite well here. Chickenpox, 85 to 90%. We will see. I didn't solve that yet. Yes, so the estimate of R0 would be 10, and since the critical vaccination is 1 minus 1 from R0, or if we don't have a perfect vaccine, it's multiplied by this factor, then our estimate of critical vaccination coverage is 1 minus S tilde. So let's assume we have a perfect vaccine for chickenpox and S tilde was 10%. So it would be the critical vaccination coverage would be 90% for the example that I just said. But here is another example for you with some different numerics and also non-perfect vaccine for measles. The numbers are applicable to measles. Okay. So a bit of repetition now. The estimate, assuming homogeneously mixing community, we have shown that so if we observe an outbreak in a community where everyone was initially susceptible, so there's no small r here, then we would estimate R0 by minus the logarithm of 1 minus tau tilde divided by tau tilde. And we would estimate the critical vaccination coverage, assuming a perfect vaccine, by 1 minus 1 upon R naught hat. So that we have shown, but then you might say, okay, so with some numerical values, you would get an estimate of these quantities. For instance, if tau tilde is 60%, this one will be close to 1.5, and this one will be close to 2/3. But then you might ask yourself, okay, how certain are we about these values? How precise are these estimates? That I will now say a few words about. Probably most people would be understand that if the outbreak took place in a small village, let's say 1,000 people, and suppose that 600 of those 1,000 got infected, there would be some uncertainty here, whereas if it took place in a bigger city, maybe 1 million people and 600,000 of them got infected, then the uncertainty is smaller. I think most people would agree to this. So that is the intuition, that the larger community, the less is the uncertainty. And if you remember, I think my first lecture, I did some simulations of the final number infected. So I simulated an outbreak in a community of 1,000 people. And I did this many times, and we saw that it could either be a small outbreak or else it was a major outbreak, and they were concentrated around a certain value. But I think I even mentioned that it looks like a normal distribution around some mean. And that is actually the case. So it can be shown that if you have a major outbreak, the final number that gets infected will be normally distributed at some mean, where tau star is the solution to the final size equation, and the standard deviation, which is proportional to the square root of n multiplied by some expression, which I call sigma squared. And this thing depends on the model parameters. I will show it on 2 slides ahead. So we can use this result to show that our estimate of R0 and our estimate of the critical vaccination coverage will be approximately normally distributed, having the correct means and some explicit standard errors. And I will now explain how these standard errors are obtained from this probabilistic result using what is called the delta method. The delta method is actually just a Taylor expansion, which I think has been taught in the first course in mathematics, which you have taken, all of you. So here is the delta method. Suppose that we have a random variable x, which has mean mu and some variance v of x. So x is a random variable. We know it has mean mu, and we know it has some variance, which we call v of x. Preferably, this variance is quite small. I will come back to that later. So if this is all we know what the mean is, and we know what the variance is. It is actually, and then we have some function of x. So this is not a density, it is some arbitrary function. So maybe we're not interested in x, maybe we're interested in some function of x. It could be the logarithm of x, or e to the power x, or x squared, or whatever. And we would like to know what is the mean and the variance of f of x. The answer is that it is impossible to say. It's not enough to know what the mean and variance of x is to say what the mean and variance of f of x is. However, we can obtain an approximate result, and that is what the delta method is about. So we assume that f is a nice function which is continuous and differentiable. Then the delta method says that an approximate value for the expected value of f of x is f evaluated in the mean value. An approximate expression for the variance of f of x is the variance of x multiplied by the square of the derivative of f evaluated in the mean of x. So actually I should have, I don't have this handwriting thing with me here, unfortunately, on my vacation, but what you do is you Taylor expand x around its mean. So if you remember Taylor expansion, you can see that x is equal to mu, f of capital X is equal to f of mu plus f prime of mu multiplied by x minus mu plus terms of smaller order. So f of capital X equals f of mu plus x minus mu within parentheses multiplied by f prime of mu. So that you write, and then you take the mean and you see what it equals. You forget the terms of higher order, and then you do the same thing with the variance, and this is what you get. So I encourage you to perform this exercise. And if you have any questions, you're welcome to ask them on the live session on Thursday. Maybe I will be back in Stockholm then, and then I will be able to write it. Otherwise, I will not have the possibility to write, but perhaps I can still explain a bit more in detail. And it is true that this approximation holds better the smaller the variance is. And what x will we have and what f of x will we have? Well, that is on the next slide. The x we will have will be tau tilde. And the f of x that we will have will depend on if we're interested in estimating R0 or estimated the critical vaccination coverage. But if you remember, R0 hat was minus the logarithm of 1 minus tau tilde divided by tau tilde. So this is our x, and our function is minus logarithm of 1 minus x divided by x. So that is our function. This is our function, and this is our random variable. And for instance, in the book that I was co-authoring, it has been shown, but it's not, the result is not due to us, but we have the result there. It says that the variance of the final size, this is not the final size, but it's the final fraction getting infected. So it is z divided by n. The variance of this thing, assuming that we have a major outbreak, is 1 over n multiplied by this rather long expressions. This rather long expression. And this tau is the limiting value, R0 is the true value. There is one more expression, that is CV squared. This CV squared is called the coefficient of variation of the infectious period. That is a complicated thing, which I haven't talked much about, but what I can say is that for the Reed-Frost model, CV is equal to 0, and for the general stochastic epidemic, which was also defined earlier in the course, CV is equal to 1. And I can also say that for most more realistic models, CV lies typically between 0 and 1. So here there is no variation in effectivity. Here there is very large variation of the infectious period, and reality is usually somewhere in between. So here we have an expression for the variance of our random variable. So remember that tau tilde corresponded to x in the delta method. So here is our expression for the variance of x, and the mean of x, or the mean of tau tilde, is equal to tau. And remember that tau and R0 relate to each other by the relation 1 minus tau is equal to e to the minus R0 tau. So this is an expression for the variance. So we know what the variance is. We also know what the mean is. The mean of tau tilde is equal to tau. And then we want to say, what is the mean of R0 hat? Remember, f of x was this minus logarithm of 1 minus x divided by x. That is simply the function evaluated in the mean value, and the variance of R0 hat will be the variance of tau tilde multiplied by the derivative of the function evaluated in the mean and taking squares. So if you perform this and do a bit of algebra, keeping in mind that R0 is equal to minus logarithm of 1 minus tau tilde divided by tau tilde. Wait for the train. This train has direction Östersund and Åre, and in the other direction it is Ånge and probably down to Stockholm. But this one might be going all the way to Trondheim, Norway. Okay, so if you do this using the expression for the variance of cont'd, after quite a bit of algebra and things cancelling out, here is the expression for the variance of our estimate. So it is 1 over n multiplied by tau, 1 minus tau, 1 plus something here. And remember that if for the Reed Frost we have CV is equal to 0, so then this term cancels out. So this is the only expression. Whereas for the general epidemic, we have a 1 here. For the general stochastic epidemic, we have a 1 here, so you get a slightly longer expression. But this was the variance. More interesting quantity is the standard error. And then you simply just take the square root of the expression. And here is sort of a constant thing, and here is division by n. Note that division of n is within the square root. So this thing is proportional to 1 over square root of n, which is what is typically the situation. If you have n observations, or of the order n observations, the standard deviation is nearly always proportional to 1 over square root of n. And if you do the same thing for the critical vaccination coverage, you get an expression which looks rather similar, but it is not, because this factor was not here earlier. So we see that this here only contains information about data, because cont'd is what the fraction getting infected in the community. R0 hat is this expression, which also only depends on how many that got infected during the outbreak. But there is one quantity, that's the coefficient of variation, which does not depend on data. And in fact, if all you observe is how many got infected during an outbreak, it is impossible to say something about the duration of the infectious period, and even less so about its randomness. So if you don't know this, you have to, that probably comes on the next slide. Yes, this thing cannot be estimated from final outbreak size data. So if you don't know anything, you have to replace it by a conservative bound. So if you take the upper value 1, you're nearly always doing something conservative, so your standard error is probably a bit too large, but that's better than the opposite. So here are some exercises. The first one is to try to show these results, at least for one of the expression, maybe the first one, to show that you get this if you apply the delta method. And here are 2 exercises to use this expression. Remember that these are based on assuming that you have a homogeneously mixing community, which is of course not fully realistic, but anyway, it is a good exercise, and it gives a feeling for how much uncertainty there are to estimates. And here you have sort of the same type of result, but being in a bigger community, you will see that here the uncertainty is smaller, as it should be. Okay, I think I will take a break here.